This is another GCSE equation practice video, and this one is power, energy and time. So I'll just recap the equation. So the equation, energy transferred, is equal to power multiplied by time. Relatively straightforward equation. And the units, in case you don't know them, energy is measured in joules, power should be measured in watts, and time is in seconds. Power, just as a recap, is also measured in joules per second. So power is the rate of energy transfer. So for example, 100 watts is the equivalent, or what that actually means is that 100 joules of energy are transferred every second. So 10 watts would mean that 10 joules of energy are transferred every second. Right, so what I want you to do now is to have a go at question 1 and 2. I'll get rid of this so you can, well, make it clearer, and then I'll take you through the answers. Remember to pause at any point if you need to write anything down. Alright, let's go through these questions then. So first one, a light bulb has a power of 60 watts and left on for 162 seconds, and we're going to calculate the energy transferred. So this is a really straightforward question. So energy is equal to power times time. So the energy transferred is power of 60 watts multiplied by 162 seconds. And that gives us 9,720 joules. Alright, let's look at the second one. So in this one, question 2, a bulb with a power rating of 120 watts is left on and uses 300 kilojoules of energy. Calculate how long the bulb was on for. Firstly in seconds and then in minutes. Okay, so let's look at this one. So again, energy is power times time. And this time we need to make time, or t, the subject of the equation. So to do that, we need to get rid of a times p. So to move times p to the other side, we need to do the opposite. So that would be dividing by p. So energy divided by power will give us the time. Now we need to be careful with the units. So we've got 300 kJ, which means kilojoules. So that's 300,000, which you have to times by 1,000, divided by the power of 120 watts. And that will give us time in seconds, which is 2,500 seconds. And then to find it in minutes, well, there's 60 seconds in a minute, so we need to do 2,500 divided by 60. And that gives us 41.6 recurring. We could just say 42 minutes. All right, let's do some more questions. So I need to have a go at number 3. So you want to pause, and then I'll take you through the answer. So this one, we've got a device with a power rating of 50 kilowatts. It's left on and uses 250 MJ. MJ, remember, means megajoules. How long was the device left on for? So energy is power times time. So to get T, we need to divide by power on the other side. So energy divided by power gives us the time. Energy, 250 MJ is 250 million. So you could write 6 zeros, or if you can do standard form, just write times 10 to the power of 6, or 6 zeros. It's completely up to you. Divided by power, 50 kilowatts. So that's 50,000. Instead of 50,000, you could write 50 times 10 to the power of 3. Both mean the same thing. And then just pop that in your calculator. And that gives us 5,000 seconds. Okay, I've got 2 extension questions now, so I'm going to pop them on for you to have a go at. So if you want to pause and have a go at these 2, and then I'll take through the answers. Alright, let's have a look. So a power station has a power output of 200 megawatts and is left on for a year. Calculate the energy supplied and give an answer in standard form. Right, okay. If you couldn't do an answer in standard, well, it will be an answer in standard form because the amount of seconds in a year is so large that your calculator will do it for you. So let's have a look. So energy supplied, so energy is power times time. So that's straightforward. And then we just need to put the numbers in. So 200 megawatts is 200 million. So you could just write 6 noughts. But instead of 6 noughts, you could write times 10 to the power of 6. Multiplied by time, now 1 year. So what we need to do, I'll do this down below. So the amount of seconds in 1 minute is 60. Multiplied by the number of minutes in 1 hour is 60. Then we need to multiply by the amount of hours in a day, which is 24. And then we need to multiply by the amount of days in a year, which is 365. If you want to argue with me and say it's 365 and a quarter, fair enough, I won't argue back, but your answer will be slightly different. So let's calculate that, and then we'll just pop that number up there. Okay? So we're going to times by 315,36000. 31,536,000. And then we're going to multiply that number by 200 times 10 to the 6, the power output. And we will get 6.3 times 10 to the power of 15 joules. Well done if you got that. And then let's look at number 5. So number 5, we've got, hopefully you've done this one. So a mass of 200 kilograms is raised upwards at 0.75 meters per second by a motor. Assuming the motor is 67.5% efficient, calculate the required input power. So this is one of them nutty extension questions. If you've got this right, well, you've either cheated or you're a genius. So, basically we need to establish what useful work this motor is doing. So if we're raising a mass upwards, we can assume that that is the useful work. So the useful work would be the gain in gravitational potential energy. If you're not sure what that is, I've got multiple videos on it, so you can go check them out if you want. So the mass is, we've got 200 kilo mass. G, you should know that, is 9.8. If you're not sure of that, I've also got a video on weight, mass and gravity. 2 videos actually. Multiplied by the height. Now we're going to do the height for a single second. So it goes 0.75 meters per second. So we can say that in 1 second, the amount of gravitational potential energy gained is equal to that. So if you put that in your calculator, that means it's taking 1,470 joules per second. You could have even written 1,470 watts if you wanted to. Well, we need that actually because we want input power. So there we go. That's the amount of power required for lifting the mass. But we've been told that it's only 67.5% efficient. So we're going to need to use the efficiency equation. So efficiency. And once again, another shameless plug. If you're not sure what efficiency is, I've got 2 videos on efficiency. One on equation practice and one that's just a basic efficiency lesson. So efficiency is useful over total. And we want the required input power. So we want the total. So I need to rearrange to get that. So I'm going to do a sneaky swap. So let's swap them 2 around. So that'll be total. Total input power is equal to the useful divided by the efficiency. So the useful is the 1,470. And the efficiency we need to do as a decimal. So you need to do 67.5% divided by 100. Then we're going to divide by the efficiency of 0.675, and that will give us the total energy or total power required, which is 2,177.7. So you could just write 2,178 or 2,180 watts. If you got that right, that's really well done. And I hope you found that helpful, and thanks for watching, and I'll speak to you soon.